My dear friends, welcome to Rajashekar classes on applied data science with Python. This is lecture number 420. In this lecture, we will try to understand gradient boosting. Now, let's look at the exact gradient boosting algorithm. By the way, we are on the page of gradient boosting on Wikipedia page. There is a very nice description of algorithm like a pseudocode. Very interesting description here. Let me explain this. What is the input? My input to the algorithm given a bunch of training set. What is my training set here? Just see this one, training set xi comma yi I equal to 1 to n, bunch of n points. Given differentiable loss function, isn't it? What are the differentiable loss functions? This could be logistic loss if it is a classification task. This could be a logistic loss if it is a classification task, squared loss if it is a regression, hinge loss. Of course, hinge loss has small problem. That hinge loss itself is not differentiable, but there are some approximations that can taken for this hinge loss. As long as loss function can be differentiable, it's good. Given this data, we want to find total model, isn't it? There is also one more thing which is given. What is this? M. What is this? My M. Just we will try to understand M. Where is this? This is M. There is also one more thing which is given capital M, which is the total number of models. Just see. What is this? This is total number of models. This is like K in, we discussed, this is, it's just like K in our system. It in the base algorithm that we discuss, this is like total number of base learners. I can say it is just like total number of base learners. Given this, let's go ahead and see how to build this. First, you have to build f0 of x. Where is my f0 of x? Just see this one. This is my f0 of x. The first base model. What is this f0 of x? I can say this is first base model. Then what would you say? Here is find a constant gamma. What is this constant gamma? Just say this one. You have to find a constant gamma which minimizes. Find a constant gamma which minimizes loss function across all of them. What is my f naught of x? Argument argmin of sigma I equal to 1 to n l yi comma gamma, isn't it? Remember, your xi comma yi I equal to 1 to n is already given. Just see, your xi comma yi I equal to 1 to n, it is already given. It is basically saying find a constant gamma which minimizes. Just see this one, what it says. Yes, let me erase. Okay. It basically says find a constant gamma which minimizes my loss over yi comma sigma. Suppose imagine my loss is squared loss. Let's say my loss is squared loss. Then what does L of y comma? What is my L of y comma gamma? Just say this one. Let me assume this is my squared loss. Then what does L of yi comma gamma equal to? Let's assume it is regression problem. It is squared loss. What does it mean? This means find gamma. Let it be regression problem. Find gamma which minimizes sigma I equal to 1 to n yi minus gamma whole square. We know that we know what minimizes. All this is optimization problem. Basically, what is this? This is optimization problem. You will get gamma equal to mean of yi. Mean of yi. You can actually derive this. Just it's a simple. You can actually derive this. If you take the first derivative. Just if you take if you take first derivative of this one, if you take first derivative like standard approach, you can take a derivative of this equal and equate it. When you end up getting is gamma is just apply standard optimization procedure, you will end up getting gamma that minimizes, gamma is constant, gamma that minimizes whole thing, which minimizes this one, gamma which minimizes, let me say this gamma which minimizes this thing is now, what is this gamma, which gamma you will get, gamma equal to mean of yi, isn't it? Now what you are saying is the first model or zeroth model. What is zeroth model? Make all yi cap. What is this yi cap? Yi cap equal to mean of yi. I can say, what is my yi cap? Yi cap is equal to mean of, let me say yi, isn't it? This is in step 2. You will learn all the models here from small m equal to 1 to capital M. You will learn all the models. Just see here. What is this? You will learn all the models m equal to small 1 to capital M. What does it mean? What is your hm of x? If I keep m equal to 1, h1 of x, h2 of x, so on. What is the maximum value of small m? Capital M. Therefore, you will get hm of x. These are our base models. What is this h1 of x, h2 of x, so on, hm of x? These are our base model. What is f0 of x? Your f0 of x is h0 x. This is f0 of x is your f0 of x is h0 of x, which is equal to argument sigma I equal to n 1 to n of yi gamma. Here iterator is m, not I. That you must understand. What is iterator here? Iterator here is m, not I. That is important point, isn't it? What is iterator? Iterator is m, not I. I will use the same notation which is here. First I need to compute pseudo residual. What is my pseudo residual? Just say this one which we discussed, pseudo residual. What is this? Pseudo residual RIM minus of dou L yi comma f of xi by dou of fxi. We learned pseudo residuals. It is negative of gradient. Gradient means what? Derivative, isn't it? Negative. Here you have negative of gradient of loss function with respect to what? With respect to f of xi, with f of x equal to fm minus 1x. What is my f of x? I can say f of x. What is my f of x? Just check here. You can check. F of x equal to f of m minus 1 of x, because right now I have already done m minus 1 stages. Why you are writing m minus 1 x means you are already done m minus 1 stages. I am at mth stage. We completed m minus 1 stages. Now we are at mth stage. At this stage I have already have a model. When m equal to 1, I already have f0 of x. When m equal to 1, what is my model? f0 of x. So I just compute this derivative. With this, I will get pseudo residual. This is exactly what we discuss. Once I get pseudo residual, I will create new training set. Pseudo residual at mth stage. Just see, pseudo residual at mth stage for ith point. Pseudo residual for mth stage. That is important. For, let me say, pseudo residual at mth stage, for ith point. That is RIM here, isn't it? What is now I will train a model like HMX. Yes, I can train a model HMX. I will train it on xi comma RIM, which is the pseudo residual. RIM is like error I at mth at mth iteration, error I at mth iteration. When you are trying to build mth model, of course, I can fit any base learners. One good example is trees. We will see what types of trees actually work. Actually work well here is in latter part of this lecture. So once you learn base learner, what is your next question? What is your final model? Your final model fm of x. Just see your final model fm of x equal to h naught of x gamma 1 h1 of x plus gamma 2 h2 of x plus so on gamma m hm of x. We got h naught done, isn't it? We got h naught done. Yes, we got h naught. We m equal to 1. We can get if I keep m equal to 1. We compute h1, isn't it? We got h naught done. We compute h1. We have to compute gamma 1. When m equal to 1, we can calculate h1. How do I compute gamma m? I can compute gamma m equal to arg min of, what is my gamma m? Just see this one. What is my gamma m? Gamma m equal to arg min of over sigma I equal to 1 to n L of yi comma m minus fm minus 1 of xi plus gamma into hm of xi. If you notice here at mth iteration, we already have fm minus 1 of x, isn't it? We already have fm minus 1 of x. We have yi. These two are constants, isn't it? We have yi. These fm1 I will repeat. If you notice here at mth iteration, we already have, just see this what is this fm minus 1 of xi. We have yi, isn't it? We have yi. These two are constants. We also have hm of xi. Gamma m equal to arg min of sigma equal to 1 to n Lyi of comma fm minus 1 of x, isn't it? This is very simple m plus gamma hm of xi. This is very simple optimization problem, and we find the best gamma that minimizes. Here the only variable is gamma. That is important. Here the only variable is gamma. So final model at mth stage, fm of x equal to fm minus 1 of x plus gamma m into hm of x. At the end of all these iterations, what do you have? Fm of x. What are your fun part here is, what is your base learners? Base learners can be where you are, each of base learners can be hm of x. Very popular thing. Gradient boosting is general idea, isn't it? Boosting is general idea, very popular idea. It's general. Gradient boosting is general idea, very popular idea. Within gradient boosting is called, there is something like gradient. Within gradient boosting is called gradient boosted decision tree, isn't it? Each of your base learners are actually decision trees. Remember, what do we want in these decision trees? We want each of our base learners. Whole idea in gradient boosting, we want high bias and low variance models. When does decision tree becomes high bias and low variance? When it is shallow, when it is depth, when its depth is small. Isn't it? When does decision tree become high bias and low variance? When it is shallow, when its depth is small. So in GBDT, in gradient boost decision tree, we do same thing as this, except the training the model on the pseudo residuals, isn't it? We train shallow decision trees. Typically we train decision trees of depth 1 2 3 4 5. I have seen cases 1 2 3 4 5, maximum 5 decision trees of depth 1. What is decision tree? The decision tree of depth 1 is called stump decision trees. Even decision stumps works very well. So unlike random forest, in random forest we have fairly deep decision trees. The deep decision trees as base learners. In the case of GBDT, we have shallow decision trees as base learners. That is important. In the case of GBDT, we have shallow decision trees as base learners, because in this case we want high bias and low variance model, isn't it? That is in GBDT. While in this case, in the case of random forest, we want low bias and high variance model, isn't it? The core difference between bagging means random forest. The core difference between bagging, I can say bagging means random forest, and boosting. This is boosting. What is this boosting in the sense? GBDT. This is the core algorithm. This is the core algorithm, and you can always refer to Wikipedia. This very simple algorithm, very elegant algorithm, especially most creative idea that I really enjoyed it. I enjoyed when I learned gradient boosting itself is a concept of pseudo residuals and the potential to reduce any differentiable loss function. This was like a magical leap of thought. I was memorized when I first saw pseudo residuals is a great way to incorporate any loss function of our choice. That's the phenomenal stroke of genius. Just go through this algorithm once or twice. If you have any difficulty, please keep a comment. This is one of the important lecture. Thank you very much.